Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button and share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright? You can also visit our website www.we-learning.in. All these sessions you will be getting there. Along with that, you will be getting session notes also. Notes for each and every lecture. You can download it and it will be very useful for you. Alright, so do check it out. Okay, now without any delay, let's get started with today's session. Today we are going to start with a new chapter, that is moving charges and magnetism, and this is lecture number 1. So I hope you are excited for the new chapter. Right? Okay. So now, here this is something which you studied in your 10th standard, if you remember, magnetic effects of current, right? So this will be more advanced. We'll be studying more in detail about it. Alright, what kind of magnetic field, what is the value of that magnetic field, how to calculate the magnetic field, how to calculate the magnetic force. All those things we'll be studying, the motion of charge, the motion of conductor in a magnetic field, all those things in detail we'll be studying in this particular chapter. All right. Now, in this particular lecture, we'll be seeing only the basics of it, because this is the very first lecture. We'll be just doing some introduction, the basics of magnets and all. Then what is magnetic field, and then Lorenz force. Lorenz force is something which is new for you. So you'll be studying, you'll be seeing this. These two things you have already seen in your 10th standard. Okay. But why I have kept these two things here? Because this particular session is for everyone, not only for above average students or toppers. It is for average students, below average, everyone. There will be some who could not study in their 10th standard because of some reasons, right? So we'll do a revision, quick revision of all these things. All right. It will be a very small lecture, not a very big lecture, because it's more theoretical. We are not going any numericals or any new concept we are not going to learn here. Okay. Now let's start. So first, magnet. What is a magnet? You would have played in your childhood with magnets, right? A lot. Magnet is something which attracts other magnet or iron-like substances, right? Something like this is a magnet. This you have played with, right? When you just throw it up, some sound will come. I played a lot with this. So then you can write magnet is any material capable of attracting iron and producing a magnetic field around itself. What is a magnetic field? Those who know, it's very good. Those who don't know, we'll come to magnetic field. Okay, complete topic this will be. Next, we'll be going a bit fast here. There are two kinds of magnets, natural magnet, artificial magnet. What are natural magnets? Very simple, from the name only you can understand. Magnets which are naturally occurring are called natural magnets. Okay, naturally occurring magnets which can attract iron. Example is a lodestone. Okay, is a naturally magnetized piece of mineral magnetite. Artificial magnet. Magnets which are made from iron in different components, shape and sizes for different uses are called artificial magnets. Okay. Now lodestone is not very much available. Okay. But there is a lot of places where we use magnets a lot. We use magnetic force a lot. So because of which there was a need to make artificial magnets, and these magnets are made of iron in different components, shape and sizes depending on the kind of magnetic field, the strength of magnetic field we need around it. All right. Examples, it's a magnetized piece of iron, steel, cobalt or nickel. Done. Next. So these are the basic properties of magnet. If two magnets are there, first of all, any magnet will have two poles. The very basic thing. One will be north pole, one will be south pole. It is not like this, it will be engraved there that it is north pole or it is south pole. No. By convention, we have kept one as north, one as south. Why we have kept it, I'll tell you. Okay. But every magnet will have two poles. Every magnet is bipolar. Every magnet is a dipole. Every magnet is a dipole. Clear? It will be having two poles. North pole and south pole. Now if I break this magnet from the middle, let's say from here if I break it, still there will be two poles. This will be south, this will become north. If I break this further, still there will be two poles, north and south. If you break it into tiny pieces also, still every magnet will have two poles. A magnet can never have one single pole. A magnet can never exist with a single pole. Alright? It can never be unipolar. Clear? So magnet will always have two poles. Now, if you keep another magnet in front of it, if north pole is in front of south pole, then they will attract. If north and north, they will repel. If south and south, they will repel. Like poles repel each other, unlike poles attract each other. Okay, very basic things which you already know. Next, freely suspended magnet. Now, suppose you take a bar magnet, you tie a thread onto it. Now, if you keep it, hang it like it, just suspend it freely. What will happen? Every time you will notice that one end of that magnet will ultimately, finally rest at a particular position. If you take it, if you rotate it also, still when it will stop, one end of that magnet will rest in a particular position every single time, in the same position. Okay, why is this so? Because our earth is also having a magnetic field around it, this we know. Okay, so whenever we take a bar magnet, we suspend it freely, one end will always align in one particular direction. Okay, so if that particular end is aligning itself towards the geographic north pole, we will call that particular pole as north pole. Alright, see, geographic north pole is the magnetic south pole in the earth's magnet, in the earth. This is an imaginary magnet. It's not a magnet. A magnet is not kept inside earth. Okay, there is a magnetic field around earth. The direction of magnetic field is such. I'll tell you how the direction of magnetic field is. Right now you can see from north to south. Okay, so the direction of magnetic field around the earth magnet is such that we can actually assume a bar magnet is kept inside. It is just assumed. Okay. So now, whenever we suspend a bar magnet freely, one end of it will rest towards one side of the earth. Now, if this end is pointing towards geographic north, we'll call this particular end as north pole. Okay, that's how the naming has come into magnets. Whenever you see a magnet, there will be nothing written on them. Okay, but like that we got to know, okay, we just named it by convention. We named it that this particular end is actually pointing towards geographic north pole, so we will name it as north. The other one will be south. Clear? And this particular concept is used in compasses also. So there will be freely suspended magnet inside a compass. So whenever you see it like this, one end will always point towards the north. So like that we get to know, okay, if we move in this direction, we will ultimately reach here. Alright? We'll ultimately reach here. This is geographic north where this north is pointing. So this is freely suspended magnet. Next, magnetic compass. As I told, what is magnetic compass? It is a device which is used to see the direction. Okay, it will every time show you north pole. You will get to know, okay, this side is north. So if you get to know one side is north, the other will be south, and the other two will be east and west. Right? Nowadays we use Google Maps to go from one place to another. We don't need this compass anymore, but still at some places like Vastu and all, they will be still using these compasses. Still a lot of uses are there. An instrument for determining direction on the surface of Earth by means of a magnetic pointer that aligns itself with Earth's magnetic field. Clear? There is a magnetic pointer inside it which will always align itself in the direction of Earth's magnetic field according to it. Alright. Now, if there is a bar magnet, if you keep a magnetic compass near to it, it is not like that this compass will only align itself towards Earth's magnetic field. Whichever magnetic field is stronger near to it, it will align itself in that way. So we make sure whenever we are seeing the direction from a compass, we do not keep any other magnet nearby. Otherwise, it will not show correct direction. Why? What happens is, this is a magnet. It is only reacting to the magnetic field. It does not know where is the geographic north and where is geographic south. It doesn't know anything. It is only reacting to the magnetic field around it. Okay. So now, if there is a bar magnet, if you keep any magnetic compass near to it, what will happen? In magnetic compass, what happens is, one end, one side of the blade will always be colored with red. That blade actually tells the direction of the North Pole, geographic North Pole. Okay. So here, if you keep this compass near a magnet, this pointer, if it is aligning itself in this direction, if it is pointing itself in this direction, that means this pole is North Pole, because this is the South Pole. North is repelling, South is something which is attracted to it, right? That means this will be North Pole, that will be South Pole. Now if you start moving this magnet, this needle will also start deflecting, will start changing its direction. Why? Because there is a magnetic field around it in particular direction, and it is actually aligning itself with the direction of magnetic field. It is aligning itself with the direction of magnetic field. I'll tell you how is the direction of magnetic field. Fine. So if you start moving it, you can see how the direction of this needle is changing as we are moving around it. Okay. So compass will also deflect if there is any other magnet, not only Earth's magnetic field. Whichever magnetic field will be strong near that compass, it will show alignment according to that. Clear? Next. Now comes the Oersted's experiment. This experiment also you have studied in your 10th standard. What is this experiment? Basically, there was a scientist, Henry Maxwell Oersted. Now this scientist, he did an experiment. Before he did the experiment, magnetism and electricity had no relation with each other. Okay? I mean, according to people, magnetism was a different thing, electricity was a different thing, completely different. Magnetism is something which can only be through a magnet. That's all. Magnetic field can be produced only through a magnet. That's all what people knew. But then this guy came into picture. What he did? He did an experiment. In that experiment, he made an electrical circuit, and then after making that electrical circuit, he kept a compass, magnetic compass near to it. The moment he switched on that electrical circuit, switched on the battery, from that battery the current started flowing in the circuit. The moment the current started flowing in the circuit, the magnetic compass showed a deflection. The switch, if we on it, this magnetic compass, if you see, it shows a deflection. The same thing happened. Alright. Now he was confused why this happened, because magnetic compass is a device which shows deflection only when there is a presence of magnetic field. With no other magnetic field, it will ever show deflection. Clear? Magnetic compass is something which will only react to magnetic field. Rest, no other field, it will show any deflection. Clear? So now he was confused that why, when I am switching this on, why this magnetic compass is showing deflection? Because the current is something which is flowing here, right? If let's say anything should happen, if any field around it should happen, it should be electric field, because this current is due to the charges. But it will not, it will never react or respond to the electric field. It will only react or respond to the magnetic field. So what he did, he switched it off. The moment he switched off, again the deflection, there was no deflection. It was normally aligning itself with Earth's magnetic field. Right? Then again he switched on, again the deflection was there. Again he switched off, again there was no deflection. So then what he did? He reversed the battery, changed the direction of current. When he changed the direction of current, the deflection on this compass, the direction of the deflection also changed. It became completely opposite. Then he started increasing the current. The deflection in this compass started increasing. He started decreasing the current. The deflection in this compass started decreasing. With this particular experiment, finally what he concluded, that whenever there is a current carrying conductor, this wire is basically a conductor which is carrying current, right? There will be a magnetic, whenever there will be a conductor which will be carrying current, or whenever there will be current flowing in any conductor, there will be a magnetic field around it. Clear? So basically these were the conclusion. According to Oersted, deflection of magnetic needle was due to magnetic field produced by the electric current. So what he told, that electric current also produces magnetic field. Any change in electric current will show a deflection in the compass. Any change in electric current means if the current is increased, there will be a deflection. If the current will decrease, the deflection will decrease. If the current is reversed, the deflection will be reversed, opposite. Okay, so any change in current will show a deflection. Electricity and magnetism are related to each other. This conclusion was given by Oersted. Okay, after that experiment, a lot of experiment happened, which actually proved that yes, electricity and magnetism are together. Electricity is something which electric current is something which produces a magnetic field. And from then, a new field or a new subject, new chapter came into picture, that is electromagnetism. That is what we are studying. Okay, electromagnetism. And there are a lot of applications of electromagnetism. The electric bell, what you see in your house, the fish kind of, right? There will be a gong, there will be a hammer, small hammer, right? This basically works on electromagnetism only. You would have seen a motor in your house, the motor which is taking water from underground to your overhead tank, that works on electromagnetism, right? There are a lot of applications of electromagnetism. So this experiment actually helped us a lot. Okay, now let's know what is magnetic field. Since then we are talking about magnetic field. Magnetic field is nothing but an influence around a magnet which is actually influencing some other magnet or some other magnetic substances. Suppose there is a magnet. I'll be going a bit fast because it's just a revision of your 10th standard. Okay, suppose there is a magnet. Around a magnet there will be some influence. See, if I keep an iron nail here very far from it, do you think this iron nail will get attracted to it? No, right? But if I bring the same iron nail near to it, it will immediately get attracted to it. Right? So why this happened? Because now I had brought this iron nail in the influence of this magnet. Okay, so around this magnet there will be something, some imaginary field. Okay, around this magnet there will be not imaginary field, actually the lines are imaginary, which we make to denote the magnetic field. Around this magnet there will be an influence. That influence is known as magnetic field. Clear? If there is a current carrying wire, around it also, if you bring an iron nail and keep it here, it will immediately get attracted to it. Try doing it once, okay? Because there is a magnetic field around it. So magnetic field is the area around a magnet in which magnetic force can be experienced by other magnets or ferromagnetic materials, etc. Clear? Area around the magnet in which magnetic force can be experienced. All right, very basic. Next, magnetic field is a quantity that has both direction and magnitude. Okay, we'll get to know about the direction also. It will have magnitude for sure, which will tell the strength, whether the strength is more or the strength is less, whether the substance will experience more force or less force. It totally depends on the magnitude of that magnetic field, right? And direction of magnetic field, it will tell in which direction the force will be experienced by some other object, okay, some other ferromagnetic substance. The SI unit is Tesla. Remember, SI unit is Tesla, denoted by B. Magnetic field is denoted by B. SI unit is Tesla. Magnetic field lines. So if this is the magnet, this is also something which you have already studied. These are the magnetic field lines around it. These are not real lines. These are just imaginary lines which represent the magnetic field. The direction is from north to south. Outside the magnet, if you see, the direction is from north to south. That means they are originating from North Pole and ending at the South Pole. Clear? Originating from North, ending inside South Pole. Originating from North, ending inside South Pole. So like this is the direction of magnetic field lines. So magnetic field lines are imaginary lines that represent magnetic field around a magnetic substance. Okay. First of all, we got to know about magnetic field by bringing any other ferromagnetic substance near to it. The moment we bring it near, it will attract. We don't have to even push it. The moment you will bring it near, it will attract. So with that, what we got to know, okay, there is some field around it. How did we get to know the direction of it? I'll tell you how you can get to know the direction. Magnetic field lines also tell the direction of the magnetic force acting on the magnetic substance. Okay. Observing magnetic field lines, how you can observe the magnetic field lines? Very simple, take a paper, spread a lot of iron filings on it, and then keep a bar magnet at the center. You will see the iron filings will get arranged in such a way that if you join or if you make lines around it, it will be, if you join these, you will be seeing a pattern. It will be aligning in a particular pattern. See here, there is a pattern around. Right? So they will align itself in a particular pattern which will show that the magnetic field lines are like this. Or what you can do is, again the same experiment was there in 10th standard also. Make an electrical circuit, or take a paper, take a cardboard kind of thing, make a hole at the center, pass the wire through that hole, and then connect the both ends of the wire through a bulb and a battery. What will happen the moment you will switch on the battery? And one more thing, on that cardboard you have to put a lot of iron filings. The moment you switch on, the iron filings will get arranged in a particular pattern. That pattern will show the magnetic field around the wire. Around the wire, the magnetic field will be like this, concentric circles. Concentric circles. This is a current carrying wire. If this is a current carrying wire where current is in this particular direction or any direction, okay, right now I'm not talking about direction. If current is flowing in it, iron filings are there on the cardboard. If current flows, the iron filings will arrange itself in concentric circles. Clear? So like this, you can observe there is a magnetic field around a magnet and there is a magnetic field around a current carrying conductor. Clear? For direction, I'll tell you, okay. So now they originate from north pole of the magnet and end at the south pole by convention. Now see, by convention, what does this mean? We have assumed it by convention. Our ancestors, whoever got to know about magnetic field, they actually told that the direction we will take from here to here. We could have taken from south to north also. Okay, there is nothing wrong in that. But by convention, we consider that the direction is from north to south. Like the direction of current is by convention. Right? The same way the direction of magnetic field is also by convention. Clear? So from north it will originate, at south it will end. See here, you can get to know by one more way also. Take a bar magnet, keep a magnetic compass near to it. We know that the magnetic compass will show a deflection where this north pole, since it is north, this will be away from it, repulsion. We'll always mark the direction of the north pole. We'll always see the direction which is towards geographic north. Alright? So that is what by convention we decided. Fine. Now take a magnet, keep it here. So the north pole will be pointing opposite. Because this is north pole, it will repel. Right? If you keep the compass here, the north pole will be pointing this side. If you keep a compass here, the north pole is pointing this side. See the red part. Here the north pole is pointing this. Here the north pole is pointing this. Right? Here if you see the north pole is pointing this. Here it is like 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 this. If I join all these directions, see how it is coming, that it is originating from north and entering inside south. Clear? Like this, we got to know the direction. First we decided we'll only see one pole. That is, what is the direction of geographic north, or this north pole, north needle. Okay? And then we'll see if I start moving this compass around it, how it shows the deflection. And we just joined that particular path. We got to know it is from north to south. This is a way of understanding the direction. Okay? Magnetic field you can observe by iron filings and a magnet. Direction you can observe this way if you want. Second, they form a closed curved loop. So now this loop is not half. It is not like it started from here and ended here. It's a complete closed curve, closed loop. How it is a closed loop? Outside it is here and inside it goes and joins like this. Clear? I'll make it with a So outside it will be like this, inside it will go and join. This also, outside it will be like this, inside it will go and join. Okay, so all these magnetic field lines will be closed loops. Now the direction, outside the magnet the direction will be from north to south. Outside the magnet the direction will be from north to south. Inside the magnet the direction will be from south to north. See, if I go like this, inside it is from south to north. Always remember, outside, remember only one, outside north to south. Inside it will be automatically south to north. Clear? So this is one such thing which you have to remember. Now the difference between electric field, magnetic field, one more. If there is a positive charge, the electric field line will originate from here, correct? And it will go to infinity. If I keep a negative charge, then it will go inside it. Right? It never forms a closed loop here. But here it will always form a closed loop. Magnetic field lines always form a closed loop. Electric field lines are not closed loops. Okay? Next, they are crowded near the poles, which show strong magnetic field near the poles. Near the poles, if you see here, if I make it like this, see the crowd near these poles. How many lines are there near the poles? If you see in this particular area, too much crowd, right? What this shows is near the ends, the strength of the magnetic field will be more. Okay? They never intersect each other. One more thing. The way electric field lines never intersect each other, the same way magnetic field lines also never ever intersect each other. Okay? Because at a single point there cannot be two directions of magnetic field. The way it was in electric field, at a single point there cannot be two directions of electric field. The same way there cannot be two directions of magnetic field at a point. They never intersect each other. I hope you will remember all these things. You already know all these things since your 10th standard. It's just a revision. Next, Lorenz force. Now this is something which is your 12th standard topic. Today we'll talk only a basic about Lorenz force. I'll just tell you what is Lorenz force. Okay? See, in your first chapter we studied about charges, right? We studied about what will happen if a charge will be kept in an electric field. See, if there is an external electric field, let's say a uniform electric field, if a charge is kept here. So will this charge experience force? Yes. Since it is a positive charge plus Q, what will be the direction of force? In the direction of electric field. I hope you remember all these things, right? So what will be the magnitude of this force? Force is equal to Q into E, correct? Force is equal to Q into E. And I can write this as F vector is equal to QE vector. The direction is same as that of E vector. So I can write this like this, correct? Now, in magnetic field what happens? In magnetic field what happens? Suppose there is a magnetic field. Now there is a charge kept here. Okay? This charge, if it is kept at rest, it will not experience any force. First thing, note it down. If a charge is kept at rest in a magnetic field, acha, I hope you can understand what kind of magnetic field are these. Magnetic field lines. These are magnetic field lines outside of the board. Sorry, inside of the board, correct? Magnetic field lines which is inside the board. Got it? If I make it like this, it will be, magnetic field lines will be like this. If I just see it, if I rotate it, these are magnetic field lines which are going inside the board. If I just rotate it, magnetic field lines will be like this, and this charge, it will be coming out. The velocity of this charge will be out of the board. Clear? I can make it like this also, where this is a positive charge kept here, where velocity of this is out of the board. It is coming out, and the magnetic field lines are in this direction. Okay? So this I have made where the magnetic field lines are inside. Magnetic field lines are going inside the board like this. Magnetic field line is like this. All these are magnetic field lines. Okay, it is going inside, and this is a charge which is moving in this particular direction, that is perpendicular. The velocity's direction is perpendicular to that of magnetic field. Okay, first thing, if a charge is kept at rest in a magnetic field, it will never experience force. Magnetic field does not give any force to a charge which is kept at rest. When we will give a velocity to this charge, when this charge will start moving, it will start experiencing force due to the magnetic field. Okay. So now what will be the direction of that force? It comes from the, I'll tell you from the formula. The force experienced by this particular charge will be Q V cross B. So this force will be vector, this is vector, this is vector, it is a cross product. From here you can understand, if this velocity is perpendicular to the magnetic field, the direction of force will also be perpendicular to the direction of this, perpendicular to the velocity. Clear? See, from this you can get to know the direction of force, V cross B. V cross B, right? What does this mean? See how you will get to know the direction of force. Take your right hand, keep it in the direction of magnetic field. Now magnetic field is, the fingers should be in the direction of magnetic field. Remember this now. Take your right hand, the finger should be in the direction of magnetic field. Magnetic field is inside. The thumb should point the velocity, direction of velocity. Then the direction of palm, the palm is upward, gives you the direction of force. Fingers in the direction of magnetic field, thumb in the direction of velocity, the palm direction will give you the direction of force on this particular charge kept in the magnetic field. So force will be in this direction. Clear? You can get to know by V cross B also. I already told how to do a cross product and get to know the direction. We'll see this in detail when we'll be doing questions. Then you will have to see, okay, in this question which direction will be the magnetic field, in this question, sorry, magnetic force. In this question, which direction will be the direction of magnetic force. It will be very interesting, very interesting. Okay. So this is the force, this is the electrostatic force, right? On this particular charge, this is the magnetic force on this charge which is moving with the velocity V. Done. This is electric field, this is magnetic field B. So now what is Lorenz force? Lorenz force is, if we combine this electric and magnetic field together, suppose in an area, in a particular space, electric field is also there, magnetic field is also there, and then we have taken a charge. Now the charge starts moving with velocity V. If we give it a velocity V, that charge will experience both the forces. See, electric force, electrostatic force will be experienced by the charge whether it is at rest or it is at motion. It is irrespective of that. It is irrespective of the state of charge, state of motion or state of rest, right? If the charge is moving also, still it will, if there is an electric field in a particular space, in a region, this charge will experience electric force, whether this charge is at motion or at rest. But if in a region there is a magnetic field, the charge will only experience force, magnetic force, when the charge is moving. Otherwise it won't. I hope these two things are clear to you. Alright. So now in a region when both fields are there, both fields means electric field is also there, magnetic field is also there. Then what will be the force? The net force, or we call it Lorenz force, will be electrostatic force plus magnetic force. Vector sum we have to do. Fine. F net, let's say. So that is equal to QE vector plus Q into V cross B vector. Clear? So this is F net, or this is basically Lorenz force. Clear? This is basically a Lorenz force. I hope you got it. Easy it is. Now, on this particular force, a lot of questions can be found. A lot of numericals, good numericals can be found. Okay, we'll be seeing certain numericals in the third lecture. Why we are not seeing the numericals here? Because the numericals will be on the motion of the charge. If a charge is present in an electric and magnetic field, in a combined electric and magnetic field, what will be the motion of the charge? The direction of motion, what will be velocity after this particular time? What will be the position after this particular time? A lot of questions, all those questions will be based on the motion of that particular charge. Right? Now, motion of the charge, right now I cannot explain, because for that I have to explain what happens when the charge experiences only magnetic field. First we'll talk about only magnetic field, then only we can talk about the combination of electric field and magnetic field, right? So in the third lecture we'll be talking about what happens when a charge is kept in when a moving charge is kept in a magnetic field. We'll be seeing certain examples of that. We'll be clearing our concept on this, then we'll bring the questions of the combination. We already know, in the first chapter we have already seen what happens when the charge is in a electric field. So this part we have already done. What kind of forces experiences, what is the motion? We have done the questions of projectile motion, this motion, circular motion, all those questions we have done, right? Now we'll be understanding this particular thing separately. Then we'll be combining the motions. Okay, in the third lecture we'll be doing that, will be again very interesting, and a lot of combinations are made, a lot of combinations. One will be, there will be two major cases. In that major cases a lot of combinations will be made. One will be electric field is parallel to magnetic field. Second, electric field is perpendicular to magnetic field. Then add some angle also, but that we don't discuss. These are the two main cases. Inside this also there will be some 10-12 kind of different cases which will be formed. We cannot discuss all the cases, some basic we will discuss, okay, so that your mind will actually understand how to solve these kind of questions. Then whatever kind of questions comes, you will be able to solve easily. Okay, clear? Remember this formula always, Lorenz Force. So today was a very basic lecture. We did a normal revision of 10th standard. We revised magnetic field again, and then we came to Lorenz Force. In the next lecture, in the next session, we'll be talking about magnetic force on a current carrying conductor. We'll not be talking about charge. We'll be talking about a conductor which is carrying current. Okay, what kind of force is experienced by that if it is kept in an external magnetic field, uniform magnetic field. Alright, so I hope you liked today's session. If you liked it, do press the like button, share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright, also visit our website www.v-learning.in. You will get all the live sessions there. Along with that, you will be getting lecture notes also, which you can download, and it will be very useful for you. All right, we'll meet up in the next session. Till then, keep learning from V Learning. All the best.